Here we have an example of an Otto cycle problem. Let us assume an Otto cycle with a compression ratio of R equal to 9:1 ratio. The intake air is at pressure at A equal to 100 kPa or 1 bar, at a temperature A equal to 20 degrees Celsius or 293 Kelvin. Its volume at point A is equal to VA equal to 500 cm3 before the compression stroke. At this point it undergoes an isochoric process from point D, so the volume at point D is also equal to 500 cm3. This volume here is the maximum volume the system can achieve. The temperature at the end of an adiabatic expansion at point D or TD is equal to 800 Kelvin. We note that the molar heat capacity at constant air pressure is around 28.19 Joule per mole Kelvin. Its molar heat capacity at constant air volume is around 20.87 Joule per mole Kelvin. Also, the ratio of molar heat capacity is around 1.4. We identify each process first: process A to B, adiabatic compression; process B to C, isochoric process; process C to D, adiabatic expansion; and process D to A, isochoric. For letter A, we are asked to find the mass of air intake. Note that the amount of gas remains the same for an enclosed system. To determine the mass of air we use the ideal gas equation shown here. We rewrite this to solve for the molar value N. Consider a point where the variables can be supplied. Based on the given, it would be at point A. Here we get that the molar value is N equal to 0.02 mole. To solve for the mass we use the molar mass equation, where for air it is around 28.97 gram per mole. Multiplying this with mole value, we get that the mass of air being taken in is around 5.794 times 10 to the power of -4 kilograms. For letter B, we are asked to find the temperature at point C or find Tc. Note that for an adiabatic process the temperature and volume ratio for 2 points is given as the equation here. We consider 2 points that have enough variables that are present, and for this case it would be points C and D, rewriting this to have an equation for temperature C. The ratio of the volume here is the compression ratio equation. We substitute the known values, we get that the temperature at point C is around 1926.6 Kelvin. At letter C, we are asked to find the pressure at point C or PC. To find the pressure at point C we use the ideal gas equation. At point C we have an ideal gas equation as shown here. The equation is incomplete and we need to find volume at point C or VC. We use the compression ratio relation. We find that the volume at point C is around 55.56 cm3. Substituting back to the modified ideal gas at point C, we find that the pressure is around 5.9 times 10 to the power of 6 pascals. For letter D, we are asked to find the heat added to the system or the QH. At this process we see that it is in an isochoric process. The heat equation at constant volume is given here. Modifying this for process B to C, we see that the temperature at point B is unknown. To solve this, we use the equation for temperature at an adiabatic condition, since at point B it undergoes an adiabatic condition, A to B process. Applying the compression ratio also, we get that the temperature at point B is around 706 Kelvin. Substituting this value to the heat equation, we find that the heat added or QH is around 510 joules. For letter E, we are asked to find the thermal efficiency. Recall, for an Otto cycle the efficiency is given by the equation here. Substituting the known values, we see that the thermal efficiency for an Otto cycle is around 58%.